Okay, a few comments and then a little bit of introduction, and then we'll dive into assignment 4. First, I recommend you watch the video, then do the MOPS. When you do this assignment, have the equation sheet handy, and you'll notice I posted the old Lab 4 document. There's useful figures and information in there for you to refer to. Also, at the end of the video, there'll be a table of contents of the times at which I do certain problems, just so you don't have to watch the whole video. If you're here just for specific problems, you can jump to the end, see the table of contents, and then go to that problem. So, as you know, if you've done the MOPS, or you need to know that a projectile means, not a general meaning, it means any object that is only acted on by the force of gravity. Air resistance has to be negligible. And an object dropped is a projectile. An object thrown horizontally is a projectile. An object thrown straight up and down is a projectile. An object thrown at an angle that does something like that. These are all different examples of projectile motion. In each case, the only force acting is the force of gravity. If an object is launched at an angle, the first thing that you always do is to find the x and y components, because you need to remind yourself that the x and y motion are different. If this is 10 meters per second at 53 degrees, then the components will be 6 meters per second in the horizontal direction and 8 meters per second in the vertical direction. And other than using this number to find the components, you will never use this in the equations. You have to deal with the x and y parts of the motion separately. And you must remind yourself again and again, this is a common mistake, that the velocity in the x direction is constant. There is no force or acceleration in the x direction. And in the y direction, the acceleration is always a negative 9.80. Don't use 9.81. Some books do it, but we're using 9.80 meters per second squared. We call that a negative g, where g is a short way of writing 9.8. And occasionally in the MOPS or in examples I give, I round it to 10. But unless told to do so, use this number as the acceleration due to gravity. And so when you launch a projectile horizontally, it starts with a v initial that is only an x velocity, and that will remain constant. When it hits the ground, it has the same x component. The y component will change, but in this case, the vy initial or vy naught equals 0. Why? Because it's thrown horizontally. It starts with no component. If you drop a ball, the vy initial is 0. If you threw it down, then it wouldn't be. Okay, so those are the key issues of projectile motion that you need to keep in mind. These are the 4 kinematics equations from the top of column 2, and these are the equations we'll be using. I got these off the internet, but so they look a little different. On your paper, it'll say Vyx final equals Vx initial plus AXT. And the reason we write the x and the y is because the x is because it must be only used for x or y. So when you do projectile motion, these equations, you have to remember ax is 0. And so Vx final equals Vx initial. And the only equation that you will use is that Vx equals delta x delta t, or any rewrite of that. So there's only one equation for the x because ax is 0. So in this case of these, the not means that time equals 0. That's the initial. And the final isn't labeled final. So when we write the equations from our equation sheet for projectile motion, we're going to change the x's to y's because the only place there's an acceleration is in the y direction. You'll see me do that. So these are the 4 equations, and you should number them on your equation sheet. These are numbered according to, in the same order as the equation sheet, and so I'm putting these here so I can refer to them when we do the problems, and I'll refer to them by number. The problems in the assignment refer to what we usually do in lab using this device. And the first thing we do is we point it straight up and down, and we launch the projectile up, and it comes straight down. There's no x motion in that case. The second thing we do is we launch it horizontally so it hits the floor. In that case, as I mentioned before, the initial velocity in the x direction is the launch velocity, and the initial velocity in the y direction is 0. If we launch at an angle, you have to find the components of the launch velocity. And what you need to know when you do the lab is that the launch velocity is independent of angle. So if this comes out at 5 meters per second, it'll come out 5 meters per second. Whether you launch it at an angle or horizontally or vertically, it will come out at 5 meters per second. So the assignment's a little bit harder because you haven't actually done the lab as we usually do when we are in a live class. Actually, I decided it's worth writing it out just so it's exactly the way it is on your equation sheet. So when you look at those 4 equations and you let ax be 0, all those 4 equations reduce to just a single equation, this one. So this is the only equation you'll ever use in projectile motion for projectile motion in the x direction. In the y direction, the acceleration is a negative 9.8 meters per second squared. And so here are the 4 equations you'll see on your equation sheet, but I've replaced all the x's with y's. Why? Because it's in the y direction. And why would I write them out both ways? Now, on the equation sheet, we wrote them in x, but you can change them to y if the problem is in the y direction. So this is what we're working with. Let's start with problem 2, actually. So problem number 2, keep in mind that these problems are all based on the lab that you're not doing. But in the lab, what we want to do is use this projectile launcher to hit a target. So in order to hit the target, we have to know what the launch velocity is. So the purpose of this procedure is to shoot it straight up and find out what the initial velocity is. That will be the velocity at which it leaves the launcher, right? When it's being launched, when the ball is in your hand, it's not a projectile till it leaves your hand. So at the point where it leaves the launcher, what is its velocity? It will then slow down, and when it reaches the top, what's the velocity at the top? The velocity is instantaneously 0. So your Vy final equals 0. That's convenient. That makes solving the problem a lot easier. And all we have to do is measure delta y. Now, if you were doing the lab, you might say, well, I need the time. But actually, we can use equation 4. And measuring the time, think about it physically. This is physics, not math. to measure the time for when this thing leaves the launcher till it gets to the top. Very difficult to do if you just do it with a stopwatch. So the idea of doing this is to eliminate the need for a stopwatch. And so we go to equation 4, and what I want you to do is take equation 4 and solve it for Vy initial. There it is. Notice that I didn't put any numbers in. You do the symbolic algebra first. That's always what we do. The Vy final is 0. When we do the algebra, this becomes negative, and we take the square root. And so now we put the numbers in. Go ahead, put the numbers. Oh, I didn't give you any numbers. Okay, there's your data. And obviously in lab we did this 3 times, right? Because we want to get an average. We want to get a good result. We want to know this initial velocity with good precision. So the method is to do it 3 times and take an average. But don't forget the 27 centimeters. So do that, put the numbers in the equation, and get your answer. Okay, if you got it, you're done. But anyway, let me just walk you through it. It's kind of a mess. I took these 3 numbers and I averaged them. And notice I kept extra digits because I don't want a rounding error. And then I had to subtract, right? We measure from the floor. You can't put the meter stick or the tape measure here. It's easier to put it on the floor. So in lab we would measure that. We would measure this. We had to subtract the 27 centimeters, which is 0.27 meters. I left the units off, and I get 2.0733 meters. And then I use my solution of equation 4, and I have a -2, I have a -9.8, and I have this number, so the negatives cancel. I might take the square root, I get 6.3747 meters. But my measurements will take this to be good to 3 digits. We want to answer in 3 digits, and so we don't want to round up. But you see, it's pretty close to 5. So sometimes these extra digits will change the result you get. You don't want to get a rounding error. But anyway, the reported answer should be only 3 significant figures. So in this case, 6.37 meters per second. Excuse me, meters per second, not meters. Okay. Okay, now that we have the initial velocity, we can easily calculate the time. So look at your equations, relationships, and see which one you want to use. Actually, you could use any of them and see what you get for an answer. Okay, I chose equation 1, but you could use any of them except for number 4, of course, because it doesn't have time in it. And Vy, notice I do the algebra first. Vy final is 0, so I solve t equals negative Vy initial over Ay. Notice I put in the unrounded number. And the acceleration is negative. This is negative. The negatives cancel. I end up with 6.048 seconds. You see how close, it's pretty close to 0.651, but not quite. So that unrounded number can make a difference in your final answer in many cases. So be careful about that. Okay, numbers 4, 5, 6, and 7 are all the same problem. It's always good practice to draw a figure and then label the figure. It will really help you solve problems. So I started that already. I drew the table and the floor and the launcher, and I labeled these distances, and I showed the path of the thing and it hitting the ground, and I labeled delta x. And the next thing I want to do is to show the vector that's the final velocity. So when it hits the ground, it's going to have a Vx final and a Vy final. And it's good to think about the problem as much as you can before you start. The other thing that you want to remind yourself, don't forget, the launch velocity is going to be Vx initial. And the Vy initial is what? 0. Why? Because it's pointing horizontally. So when it leaves the launcher, it has no vertical component. So you have to know all this to solve the problem. And we are going to have to find that final vector. So I'm going to label this angle at which it hits, theta. And notice it's a negative angle because it's clockwise from x. So that's good. That you should always do this. Get used to drawing good figures that are well labeled. It's really important. So keep in mind, we do actually do this in lab. We set this up on a table, we take these measurements, we launch it, we put a piece of carbon paper on the floor so it makes a mark so we know exactly where it hits the floor. And then we measure that delta x, and we measure these distances. And so let's think our way through the problem. So the initial velocity is the x velocity. It doesn't change. So the x initial and x final are going to be the same. Remember that. And we have that equation up there, right? The only equation. So to get the Vx, it's going to simply be delta x delta t. And so logically you'd say, okay, let's measure the time with a stopwatch. The problem is, like the last one, in the lab it's going to be very difficult to measure when that launches and when it hits the ground and get a good measurement. So we use our knowledge of physics to get the time, because it turns out that the time only depends on the height because we're launching it horizontally. So go to your list of equations and see which equation you can use to calculate the time from known measurements, not to measure the time. Take a look and see if you can find that equation. So the best one to use is number 3, delta y, which we know is Vy initial t, which is 0, plus 1/2 AYT squared. This is another example of where the x and the y are independent, and so the only unknown is the t. And it would be solving a quadratic except the Vy initial 0. And so when you solve for t, you get that t equals 2 delta y over ay square root. Plus or minus, of course, it's going to be the plus value. Okay, so now you can calculate the time. And with the time and the delta x, you can get the initial velocity. If you go to the lab document, you'll see the figure and this analysis all worked out in the posted lab document for the actual lab 4 that we usually do in class. Okay, do the calculation and let's see if we both get the same time. Okay, so I added the 117 and the 27.5 and I put in 144.5. Oh, but it has to be meters, so I made a mistake. So let me move the decimal point. And then I multiply by 2 using the equation that I deleted and divide by 9.8 meters per second squared. And you see the meters cancel. And 1 over second squared, when you take the square root of the number, you take this. But, oh, this should be negative, another mistake, and this should be negative. If you put this in negative, you can try and take a negative square root, it won't work. So there's all these places you can make mistakes. Why is the delta y negative? Because it goes down. Y final is 0, and y initial is the 1.445 meters, right? So it's a negative delta y. So you end up with a positive number in the square root. And when you take this time and bring it up here, and I'm not going to round it, and then divide it into the delta x, then you get 9.0048 meters per second as the velocity, but we're going to round to 3 digits. So the final answer that you're going to put in the box would be 9.00 meters per second. Okay, on to number 5. Oh, great. We already answered number 5. Just remember when you put it in, do 3 significant figures. So now we can do 6 and 7. And looking ahead, we need to get the speed at which it hits the ground. So that's the magnitude of this vector. And we need the angle. So to get the angle, right, remember that, I hope, inverse tan of the y component over the x component. And what do we remember? We remind ourselves, easy to forget, watch out, this velocity is constant. We know what that velocity is. We just need to find the Vy. And so when we find Vy, we can get both the magnitude of this vector and the angle. So we have Vx. Let's find Vy. Go to your equations and find Vy. Okay, what did you find? Well, you found that either one of these is good. This would be I just go to the first one and use it. You can't use this because it doesn't have Vy final in it. And you could use this, but this will be less work, or this one. So let's take equation number 1 and find Vy final. Okay, there it is. Notice how I do it. I do the expression first, then I put the numbers in, Vy initial 0, don't forget that. And you may find it annoying to write in all these y's, but it's a reminder that you're not mixing, you don't ever mix the x and the y. And believe me, some of you will make that mistake. So Vy final 0, 9.8. I couldn't fit the time in there, but we know the time is 0.5430 seconds. I put that in there and multiplied it. And notice it's negative, and it should be negative. Okay, now we need to find the speed, which is the magnitude of this vector, and the angle. And we'll find it as a negative angle. And so which equations do you use for that? You should know those. Hopefully you know them without looking. But anyway, look at the equation sheet if you don't know, and identify the 2 equations to get the magnitude and the direction of the final velocity. So there are your 2 equations from your vector equations. To find the magnitude of a vector, you take the 2 components and you square them and take the square root. And be careful, we're finding, because it's easy, you got a lot of vectors and a lot of components, we're finding the magnitude of this, so there's the x component. Don't use the initial, use the finals. And Vx final is the same as Vx initial, right? But Vy final, we just found that here. And the Vx doesn't change here. That all goes in there. And I didn't do the calculation, I'll let you do that. And the angle is going to be the y component, that, negative, over the x component, that, positive, and you'll get a negative angle, which is what you want. And you can see I can see the y component is smaller than the x component, so it's going to be, my figure is misleading, right? The x component is 9 and the y component is only 5, so you can see the angle is going to be less than 45 degrees. Okay, next problem. Okay, notice I spent quite a bit of time drawing a carefully detailed figure. Now you have it, but it's good to practice drawing things, and the figure you have doesn't have all these labeling. So it's also good to think ahead as to what's going on. So notice I drew in the vector. It's launched at a certain angle. It is going to have an x and y component, right? Because now we're launching at an angle. So the x initial is not 0 and the y initial is not 0, like in the other two problems. And then it's going to go in a path and it's going to land like the last one. It's going to have an x final and a y final and a direction and a magnitude. So I drew all that in and I gave you the numbers for the problem I'm going to do. The initial velocity is this, the launch angle is this, the height of the building is this. And then looking ahead, the first question is, what's the maximum speed? At what direction does it land just before it touches the ground? What's the time of flight? What's the maximum height that it reaches at its highest point? And I added a question calling it 11b. How far downrange will it land from the base of the building? So let's find all those things. First of all, maximum speed, it's going to go up, right? The x component stays the same, but the y component is shrinking. So this is where the speed is minimum, if you think about it. Remember, x is going to stay the same, so the speed will be the x plus the y. And as it goes up, the y is getting less and less, so the speed is shrinking. But it doesn't go to 0, right? At this point, it still has this amount of speed, whatever that is. And when it lands, it's going to have the same x speed, right? Because ax equals 0. I can't remind you of that enough. Easy to make a mistake. And then as it's come down, the y component is growing. So when it gets to this point, it's going to be going down at a 30-degree angle with the same speed that it has here, but then it's going to go faster and faster. So obviously, I think it's obvious, the maximum speed is going to be down here. And so the maximum speed will be the magnitude of the final velocity. And we just did that, so we know how to find that, right? This squared plus this squared, square root. And that's the first question, number 8. And number 9 is the angle, and we know how to find that because we already did it. But we have to find these two things. So the first thing you want to do, no matter what, is find these components, and then don't use this again, right? This is another common mistake, is to use this in these equations. So the Vx is easy. We just use the component equation. And the Vy initial is easy. And the Vx initial is the Vx final. But we got to find this. So go ahead, let's start by getting the components. Okay, hopefully by now you can do this without thinking. The Vx initial is just going to be the V initial times the cosine of the angle 30 degrees, and that's what I got, and I wrote that down here so I can save it. And then the Vy initial is the V initial times the sine of 30, which is a half. So we get exactly 12 meters per second. And just before I forget, I'm going to write this down here, remembering that the Vx doesn't change because there's no acceleration in the x direction. And so I write that right down here so I don't forget it. And now to get the magnitude of this and the direction, I got to find the y component of the final velocity, the Vy final. And we have the Vy initial. And here are our equations. So figure out how you're going to get that Vy final. I want you to look at these equations and think about it before you see what I do. So there is more than one way of getting that Vy final. The most direct way is, since we don't know, we're going to have to find the time. So we could find the time and then find the Vy final, but that would be 2 steps. But that's okay because we need the time anyway for question number 10. But I'm just going to do it directly. Since we don't have the time yet, we can use equation number 4, right? Just remember, that's the one without time in it. So let's use this equation to find Vy final. Okay, this should be straightforward enough, but there are some tricks, some pitfalls here that you got to worry about. So take this equation, take the square root of this, and then put the numbers in. So this is Vy initial squared. This is my Vy initial squared plus 2ay delta y. So here's where you could mess up. You put in 2, you put in a negative 9.8. If you put in 20 for delta y, this number will be negative. You'll subtract it from this, and you'll actually get a negative number to take the square root of, and that's sort of a sign that something went wrong. But delta y is negative 20, right? Because y initial here and y final is here. And you may get confused. You may think the delta y is this. But no, this is where we start. This is where we end. Y final is 0 minus y initial, which is 20, is a negative 20. So it went down 20 meters from the start to the end. What this is irrelevant, actually, although we will have to find it. So anyway, we end up getting 23.15 meters per second. Now you can use the physics. Supposing you made this mistake, two things could happen. One is you'd see a square root of a negative number. If you ignored it and took the square root, you would get something that would be too small. So clearly, if the initial y is 12, when you get to this point, it's going to be negative 12. So when you get to this point, way down here, 20 meters, it's got to be considerably larger than negative 12. And yes, this is negative. I put the negative sign in. Okay, so we're using the math and the physics. We're doing physics to make sure to watch out for mistakes. This is reasonable. Given we started with 12, we got here negative 12. This seems like a reasonable number, so I trust it. And so we have 20.785 for the x component, 23.15, negative 23.15 for the y component. Now we can find the magnitude of the final velocity and the direction. Let's just get those numbers so that we're sure that we're doing the math right. Okay, this is what I'm getting. Square those two numbers and I get 31.11 meters per second. And I get, for the angle, negative 48.08 degrees. That would be 40, you'll report it as 48.1 degrees, negative, remember it's negative. And then we check our answers. Notice, this is important. It's easy to make calculation errors, parentheses, a minus sign. So what I'm noticing is that what I'm looking for is that this 31.11 is bigger than these two numbers. So I have a 20-something and a 23-something. 31 for the magnitude makes sense. Okay, if I got something that was smaller than the components, I know there's a math error. Also, I'm noticing that the y component has a larger magnitude than the x component. And if this is larger than this, what does that mean about the angle? This is your trig. It should be bigger than 45 degrees, and I'm getting 48.08 degrees negative. So these results, they make sense physically, so I'm going to go with it. Okay, now the last three things, the time of flight, the maximum height, and this extra thing, the distance. So let's find the time of flight. Where do you go? You go to your equations and see which one will be convenient. So I chose equation 1. I did the algebra. Notice the method. And now we just got to put the numbers in. But be careful. Easy to make a mistake. All right. Get the number. Okay, did you get this? 3.587 seconds. That's from here to here, the time of flight. If you didn't, you can find your mistake. VY final is what? Negative 2315. Negative. VY initial is what? 12. So you have negative 23.5 minus 12, right? Those are both negative. And what is this? Negative 9.8. So all these numbers are negative, and this is a positive number, but there's a negative sign. And so it ends up being positive, this number. Now you can also use the physics. If you understand how projectiles work, watch this. The time depends on the y velocity and the height, right? You should realize that. And if you start with 12 meters per second, since g is almost 10, it's going to take about 1.2 seconds, right? Because it's going up. If it starts at 12, after 1 second, you subtract 9.8. So this is about 1.2 seconds going up. It's going to be about 1.2 seconds getting back to here. So we're at 2.4 seconds just to get back to this height. And then we have the rest of the time. And so this answer of 3.587 seconds seems quite reasonable. Okay, now H max. And remember, this time is from here to here, not this time, so you got to be careful. How are you going to get that H max? So hint, again, this time, 3.58 seconds is for here. You can't use it here. No reason to find this time from here to here. You could do it in 2 steps, but just use this equation, right? Since we don't know the time from here to here, use this equation, but be careful. So using this equation, you have to notice that the VY initial, when you're up here, we're going from here to here, that's the height we want to find. The VY initial is 0. You do not want to use this. And given that this starts at 0 and goes down, remember, we're just doing the Y part. We end up with this equation. And this number will be the final velocity, but it's squared, so it'll be positive. 2 times negative 9.8. You are going to get a negative delta y. The delta y that we're finding is negative, but it asks for the maximum height. So when you report it, because of the way the question is worded, you report it as a positive number. Let's just get what that number is. Okay, I got negative 27.34 meters, so the maximum height is 27.34. And of course, this is easy to check. It better be bigger than 20, and yet it better not be too big, right? If you get 270, or even if you got 50, it doesn't make any sense, because it's not going to go up very far before it comes down. And so this makes perfect sense. It goes up about 7.34 meters above the building height before it comes back down. So there we got our delta y. And then the extra question I threw in is the delta x. Do you know how to get that? Get that number. See if you can get it right. Okay, there's your bonus question, right? The velocity in the x direction is constant, so the delta x is simply vx times the time, the full time of flight. And so that's the answer. You would report it as 74.6 meters if there were such a question. And last, the table of contents. So if you need a specific problem that you're stuck on. But anyway, this is, we're not just out here, right? The assignments are designed to help you learn. So don't just do them to get points and not understand. Push yourself to understand. So there's a lot of explanation and reasoning woven into these. it might benefit you to watch some of what I did, even if you've already done them and got them correct. Good luck.